Hi class, this video is on topic C3, Coulomb's law and electric fields. We've just finished our chapter on gravitational fields and now we're going to start our chapter on electric fields. And there are some similarities and differences between gravitational force and electric force, and this is a big learning goal. So by the end of this video, and throughout this chapter, we're going to work on being able to list the similarities and differences between gravitational and electric force fields, explain the relationships outlined in Coulomb's law, demonstrate an understanding of the concepts of electric force, electric field, and analyze and solve the quantitative problems related to this, and interpret and draw electric field lines. So hopefully you'll recall in grade 9 in the electricity unit in the static electricity chapter, you learned about the law of electric charges, that charged objects exert forces on one another that obey the following rules. Like charges repel, unlike charges attract, and charged objects attract some neutral objects. And this law tells us the direction of this attractive or repulsive force. So it tells us if it's attractive or repulsive. But in grade 9 electricity, you didn't quantify the strength of this force. So now this is what we're going to move forward doing. So first, the electric force is a force that acts between two charged particles. It, like all forces, has magnitude and direction. It is a non-contact force that depends on the object distance, like the force of gravity. And it can be attractive or repulsive, unlike the force of gravity. So gravity can never be repulsive, only attractive, but with electric force, it can be both attractive or repulsive. So for example, there is a repulsive force between the two negative charges here, and object A is experiencing a repulsive force to the left, and there's also another force pushing object B to the right. And this is an example of the action-reaction pair as per Newton's third law. And similarly, there's an attractive force between this positive and this negative point charge, and these also make up an action-reaction pair. So the first piece of Coulomb's law is that the strength of the electric force is directly proportional to charges. So we say Fe is proportional to Q. So we take a look at, this is one of the simulations that I linked to in below. If we take charge 1 at negative 4 microcoulombs. So micro is times 10 to the minus 6. So that means 4 microcoulombs is a million times smaller than 4 coulombs. So it's a small charge. And that negative 4 microcoulombs produces, with this positive 6 microcoulombs, at this distance produces 240 newtons. If we go over to here to double that charge, we can see that these force vectors have increased. They've doubled, roughly doubled. So 480, roughly 480 newtons. So directly proportional means that when charge doubles, electric force doubles, and this relationship is analogous to mass and force of gravity. So if a ball is held above the earth, and then if the ball's mass doubles, the force of gravity doubles. And then the next relationship outlined in Coulomb's law is that the strength of the electric force is also inversely proportional to the square of the separation distance. We also call this center to center distance. So inversely proportional means that if distance doubles, so if this denominator doubles, then the electric force goes down by 4 times. And this relationship between electric force and distance is the exact same as that for gravity, because we remember we have r squared in the denominator of the Newton's universal law of gravitation. So for example, here we have these 2 point charges, positive charges that are separated by r. Now if the distance is 2r, the new force will be 1/4 of the old force. And mathematically, Coulomb's law states this equation here. We've got Fe equals KQ1Q2 over R squared, where Fe is the magnitude of the force in newtons. Q1 and Q2 are the magnitudes of the charges on each object in coulombs. R is the center-to-center distance between those charges. K is Coulomb's constant, 9.0 times 10 to the 9 Newton meters squared per Coulomb squared. So this is a new constant. And I guess one thing to note, I've mentioned before that orders of magnitude can be something that is a common mistake in this unit. So our gravitational constant was times 10 to the negative. So it was a really small number. Coulomb's constant is a very large number. So you do not have to memorize the value of the constants or the units, but you have to know which values to pull from which resources by the end of the unit when all the problems are mixed together. And just notice how similar Coulomb's law is, the equation for Coulomb's law is to Newton's law of universal gravitation. So the charges of two objects are here instead of the masses of two objects. And we've got the center-to-center distance squared in the denominator. Note that to use this, we're assuming that the charges on the two spheres are very small. The two spheres are small compared to the distance between them. And so that's valid when we say point charges, or if the spheres have a perfectly even charge distribution. And the term point charge, I'm using air quotes here, is used in physics when we think of all the charge concentrated in the middle, and that way we don't have to think of the spatial distribution of the charge. So the statement of Coulomb's law in words is the magnitude of the force between the 2 point charges is inversely proportional to the square of the distance between the charges and directly proportional to the product of the charges. So notes, this equation, we are going to use it for finding the magnitude of the force. Use the magnitudes of the charges, not the signs, when you sub into Coulomb's law. We're going to use the law of electric charges, which is, most people would say, is very easy to find the direction. So there is no need to sub in the negatives. We're going to state together as a convention, we are going to be using the magnitudes of the charges to get the magnitudes of the forces. The forces on the two charges are action-reaction pairs, as per Newton's third law, and a charge is considered to be concentrated at the center of the sphere for modeling purposes, called a point charge. So all but one slide in this lesson is considering point charges. So like any force, electric forces are vectors, and we must use vector sum if we want the total force. If there are multiple electric forces, we need to add those together using vector algebra. I guess I should mention, if we're more than one dimension, then you're going to be considering vector sum. And we have trigonometry or vector components to deal with that. If it's one dimensional, then scalar addition and subtraction. You consider the direction, but it ends up being mathematically just addition or subtraction. So this is relevant when we've got two-dimensional electric force problems. So let's try an example. What is the magnitude of the electric force between two spheres 5.2 meters apart if each has a charge of 3.6 nanocoulombs? So we're going to start with the diagram and draw that it's 5.2 meters. We're going to label the charges. Now, nanocoulombs. Nano is 10 to the 9 times smaller. So I guess 10 to the negative 9. 3.6, what would that be? Trillion times smaller than 3.6 coulombs. So 3.6 nanocoulombs. So you just do 3.6 times 10 to the minus 9 coulombs to get rid of the N, to get rid of the nano. And then what's the direction of this force? So we've got our equation for force, KQQ over R squared. We've got our diagram. In this case, a free body diagram is, if you forget about the free body diagram, it's not critical, but it is always a good idea. So there's the assumption here that these tiny charged objects are not enough mass to consider the force of gravity, and we're looking for the direction of the electric force anyways. So electric force is our new Coulomb's constant times one charge times the other, or you could do this squared since it's the same charge, divided by 5.2 meters squared. So we just do a quick unit analysis here to check if it gives us newtons that we want. So coulombs squared on the top cancels with coulomb squared in the bottom. You've got meters squared in the top and meters squared in the bottom, and we're left with newtons. So the calculation will be the same because we don't have to do it twice. If both charges are positive, then the force of A on B is 4.3 times 10 to the minus 9 newtons to the right, and the force of B on A is 4.3 times 10 to the minus 9 newtons to the left. Okay, so another example. Calculate the net electric force. I guess I just mentioned, I don't know if you were given the diagram for example 1. When it says what is the direction of this force, I would accept, if you have a nice diagram, I would accept the arrows instead of the words right and left. Or, you should always have a diagram, but you could also say away from each other if they are both positive, towards each other if they're both negative. So in example 2, this is different because now it's the net electric force. So net is a word that we use for vector quantities when they need to be added together. So net, total, sum, resultant, those words all indicate they're doing the same kind of vector components, vector addition. So we have 3 point charges, and we want to know the net electric force on charge B. So it says net electric force because B is going to be pulled to C, to the right, but also pulled to the left to A. We'll draw our diagram, label our givens. I believe it's already given. And just kind of do some prep work for your common sense check. So guess, is B going to go to the right or the left? So if we take a look at, well, R squared is, because R is squared, it really has a big effect. So my guess is that this one would win based on being closer. So it would move to the right. And then it turns out I also look at the charge values, and this is also a stronger charge. So this is going to be a stronger attractive force to the right. And we're going to subtract a smaller attractive force to the left, and to the right is going to win. So let's work out the math. So here we need a free body diagram for B. So we have the force of C on B, because remember, for free body diagram B, we put the forces on B on the free body diagram for B. So it's the force of C on B, and then we've got the force of A on B. This is the only free body diagram that we need. But if we did want to draw a free body diagram for C, we would have an attractive force to the left, and it would be equal size to this red force. It would be force of B on C. So calculating this red force, I guess we'll do this blue one first, F of A on B, KQQ over R squared. Hopefully we're very comfortable using the exponent scientific notation buttons on your calculator so that you're not doing times 10 to the every single time. So 9 EE9 times 4 EE minus 6 times 2.7 EE minus 6 divided by 0.2 squared. So we get 2.43 newtons to the left. And now for that red force, we'll calculate by substituting in our values. So it was really important that we had a nice, neat diagram so that we subbed in the right values. Again, we see that micro, which is times 10 to the minus 6. So 6.4 times 10 to the minus 6 regular coulombs. So once we sub that in, we get 15.552 newtons to the right. We've got F of A on B plus F of C on B. But since we're adding force to the left plus the force to the right, we're going to need to switch one of the signs, and then we switch the direction with the sign. So that's how it ends up being a subtraction. So let's say if we said to the left was positive, so if we did 2.43 newtons minus 15.552, we're going to use unrounded numbers here, and we'd get a negative number, but negative means to the right based on our convention. So we know our answer is 13 newtons to the right. Okay, one step more challenging. Calculate the net force on charge A in the diagram. You do have a practice question where it's a little bit more complicated geometry like this. So draw our diagram, label our givens. Then, since we're doing a net force calculation, you need a free body diagram for the object of interest. So A is of interest. A is of interest. So the free body diagram of A, we have B that is pulling it to the right. So the force of B on A is pulling to the right. We've also got D, so there's the force of D on A pulling it downwards. So those are both attractive. And then we have the repulsive force from C. Now it is farther away, so it's not going to be as big, given that the charge values are the same. It's all 2 microcoulombs. But it's farther away, so it's not going to be as big, but it's still going to be, you're still going to have to consider it in the calculation because it's going to add to, or no, sorry, it's going to take away from what these can do. So we sub in for Fe equals KQ over R squared for both of these numbers. So the blue force down, we get 3.6 newtons. The black force over, we get 3.6 newtons. And then this diagonal force here. So I think it's clear, but just in case it's not. So when we're doing this repulsive force here, Q1 would be this, Q2 would be this, 2 microcoulombs. It doesn't really matter which is which because multiplication is commutative. The order doesn't matter. And then divided by R squared. Now, how do we get that diagonal distance if we know from here to here is 10 centimeters? Well, that's the Pythagorean, or that's the hypotenuse of a right angle triangle. That's also isosceles right angle triangle. So it is 10 squared plus 10 squared, square root that. We get 14.142 centimeters. So that's what goes into our denominator in SI units. And we get 1.8 newtons up to the left. Now we're going to add these 3 vectors to, I guess there should be vector arrows on all of these. So vector sum, a force to the up to the left, a force to the right, and a force down. So we have to use some vector components here. Now, if you want to create a table and one column is X component, or so each row would be each force. And then there would be an X column, X component column, and a Y component column. You could do it like that, or if you can already see how this works, you can use the statement right away. So Fx, we've got the horizontal component of this, which is 3.6, I guess. Oh no, so 3.6 is this, 3.6 minus, well this is 0, so it's just minus the horizontal component here. So 1.8 cos 45. So it's nice that it is actually a square so that you don't really have to do any work to find the 45. If you did have to do work to get that angle, you'd have to do tan inverse of this angle here, or this angle here, depending on how you want to solve for it. So using our components and tan inverse if we need to, then we can find that the answer is 3.3 newtons down and to the right. Okay, so just before moving on, let's just take a moment to compare. So the mathematical equations for Coulomb's law for electric force and Newton's universal law of gravitation for gravitational force. There are a lot of similarities. Okay, so for electric force, we use Coulomb's constant. For universal law of gravitation, we use the universal gravitational constant. We use charges, the 2-point charges, instead of the two masses. And the other difference that's obvious in this graphic is that Fe can be attractive or repulsive, whereas force of gravity can only be attractive. They are both calculating for a force in newtons. We do care about the total direction, or the direction if we're finding a total force. They both are inversely proportional to the square of the center to center distance. Okay, so now that we've learned about the electric force, let's learn about the force fields. So funny story, you know how some songs have famously misheard lyrics, like Taylor Swift's Starbucks Lovers? Well, this catchy song is one that I've misheard for a long time, and it's called Electric Feel by MGMT, but I've always heard it and sang it as Electric Fields. I actually have a little science playlist on Spotify that the songs that have titles that are sciencey. So I went to add this, and that's when I discovered that I had the title wrong. But maybe I'm not the only one that has made this mistake before, because I went to YouTube and I typed electric field because I wanted to find a good video for you as an extra resource, and this video came up. So maybe it's not just me. This would be a good exit ticket, by the way. But first, before we talk about the electric fields, let's just review what we know about gravitational fields. So with gravitational fields, an object with mass creates a gravitational field in the space surrounding it. So the Earth creates this gravitational field. And then when a second object with mass is placed within this field, so this is an object here, it will feel a force of attraction. And then to calculate this force of attraction, we can multiply the object's mass with the gravitational field strength at that point. So Fg equals mg. Now I've made lots of points to say, well, this is only true if you're close to the Earth's surface. Well, if you're close to the Earth's surface, then you can use 9.81. If you know you're hundreds of kilometers out and like you're at an altitude of an international space station, as long as you actually know the gravitational field strength at that location, you can still use this equation. We may also calculate this force using Newton's law of universal gravitation. So if it's not like Earth and we don't, we're given the mass and the radius, but it's not, it doesn't all get bundled together into this convenient field strength value, then we can use the universal law of gravitation. And by combining these formulas together, we can isolate an equation for field strength. So how strongly is an object with mass being pulled towards the center of a planet? So it's universal gravitational constant times the mass of the planet divided by the center to center distance squared. And the gravitational field strength at any point describes how much force is felt by 1 kilogram of mass that is pulled directly towards the center of the planet. It's a vector quantity, so we care about that center, the direction to the center. And okay, now compared to the gravitational field, the electric field, so we give it a symbol epsilon, which is kind of like a curvy E. I think it's Greek letter lowercase e, or it might be capital E. And we put an arrow on top of it because it is a vector quantity. An electric field is a region in which a force is exerted on an electric charge. So let's say we have a charged object that is far away from other charged objects. It creates an electric field in the space surrounding it. And if another charge, like this red small charge were to enter this region, the electric field would exert a force on it. So if we had a very small positive charge to test out this electric field, we can see that this is the force is all outwards, radially outwards. So just like gravitational field exerts a force on a mass that is placed within that field, the test charge is experiencing a repulsive force when it's placed within that field. But this is repulsive. Gravity is always attractive. We could also have, if the source of the electric field was negative, our field lines actually point towards the center because a positive charge travels to the center. So just by convention, the fact that we choose positive it doesn't really matter. It's just what the convention is. So we are going to use a positive test charge, and it always moves towards negative, away from positive. So we say electric field lines move positive to negative. And you might be wondering, what do I mean by a test charge? So a test charge is a very small positive charge, and it's a charge that's affected by the field so that we could use it as a test, I'm using air quotes again, for the direction and the magnitude of the electric field created by the other object. So as compared to those 5 points with gravitational fields, look at how those exact same statements apply with small changes in the words. So any object with charge, not mass, any object with charge creates an electric field, so electric field, not gravitational field, in the space surrounding it. When a second object with a charge is placed within this field, it will feel a force of attraction or repulsion. And notice the direction is not always towards the center. It's towards the center if it's a negative charge, but it's away from the center, like radially away from the positive. To calculate this force, we can multiply the object's charge by the electric field strength. And we may also calculate this force using Coulomb's law. So depending on what you have, if you have epsilon, you can use this equation. If you have the two charges and the distance between them, you can use Coulomb's law. Just like with the gravitational equation for force, I like to use capital Q for the bigger of the two charges, just to avoid confusion with numbering Q1 and Q2. And then the fifth, oops, where's my, here we go. Electric field strength, epsilon. So by combining these formulas together, so if we combine Fe equals Q epsilon and Fe equals KQQ over R squared, if we combine those two, we get epsilon equals KQ over R squared. Now this is the bigger of the two charges, not the test charge, because the test charge has a very small charge. It's like the equivalent of the analogous of the mass of the planet. And this is for a point charge. So all of the charge is concentrated at this one point. We don't have to worry about spatial distribution of the charge. And the electric field strength, using this equation, you can actually see a bit better what the units are. It's newtons per Coulomb. That should remind you of when we had the same equation for gravity. So here we sometimes rearrange G and said it was Fg over m, newtons per kilogram. So newtons per kilogram was for gravity, and newtons per Coulomb is for electric field strength. This is a vector quantity, and it's a direction equivalent to what a positive test charge would do. So if we had a field lines map, it would tell you the direction of epsilon, and it tells you what would happen to the positive charge. So let's do an example. So determine the electric field strength 15 centimeters to the right of a positive charge of 3.6 nanocoulombs. How would the electric field strength be similar or different if the charge were negative? So this is our actual charge creating an electric field strength. This is just a test charge to tell you that we're 15 centimeters away. So we don't need to know the whether this is positive or negative. So we know Q is 3.6 times 10 to the minus 9 coulombs. That's how you deal with a nanocoulombs. And then radius is 0.15 meters. Don't forget to convert to SI units. And then we know epsilon equals KQ over R squared. We sub in our values. Oh yeah, this is one thing I wanted to mention. Sometimes in the slides or the textbook, they use 9.0. And I prefer to use 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. The difference would be 2 sig figs or 3 sig figs. So you can use either, but you have to be careful to round your answer to the correct number of sig figs. So if I use 9.0 here, and this was 3.60, this was 0.150, I'd have to be careful to round to 2 sig figs, because just remember that these constants are experimentally determined values and the sig figs needs to be considered. Okay. How would the electric field strength be different if the charge were negative? So that's if this charge were negative, we would use all the same numbers, we'd get the same answer, but the direction would flip. Because now if it was positive, if this was negative, the point charge would want to go towards it. But notice when this is positive for part A, the answer for our direction is to the right. Epsilon is a vector quantity. Electric field is a vector quantity. So you need to put in a direction for full marks for these problems. Okay, so for drawing electric field diagrams for point charges, it's important to know how these lines will interact with one another. So we always start from the positive and end at the negative. They do not overlap. They extend forever. And they also show density of the lines shows the strength of the force. So for example, being here is greater force than being out here. As well, here is a dead zone where you're not going to feel a force. Here is a stronger force moving a positive test charge that way. Here is a weaker force. You might feel deja vu from the magnetism lessons from grade 11. And that is in fact the next chapter. So there you should see the electric field line rules follow the field line rules for the other force fields as well. So let's just practice drawing, or I'm going to ask you to practice drawing. And this is how they would look. So you start with maybe radially away from the positive and towards the center of the negative, because this is what a positive test charge would do. And then they will interact because it's the vector sum. The total force here is the vector sum of that one plus that one, or sorry, that one. So if you add that force, the force going this way, together with the force going that way, the vertical components cancel and you're only left with horizontal at this point here. So they bend. They bend when they're interacting with others, with other objects with charge. So the vector nature of electric fields, it's similar to the electric force. Electric fields are vectors, and the net electric field is the vector sum of individual electric fields. So for example, calculate the magnitude and the direction of the electric field at point C in the diagram below. Now point C, if it was placed here as a positive test charge for this negative, it would move there with a certain force because of its electric field strength. Also, this one has electric field lines moving it that way as well. So it's going to get an extra push to the left. It's going to get a pull to the left because of this negative, and it's also going to get a push to the left because of this positive. So we're going to find epsilon based on this and based on this, and then we're going to do vector addition. Oops. Okay, so we've got KQA over R squared. It's really useful to use the subscript. So epsilon A, that would be the electric field strength because of being close to this negative. And we get that value in newtons per coulomb to the left. We use our diagram and law of electric charges in order to find that sign. It's not because it ended up being positive, because we always use the magnitude of Q. So a test charge is always positive, this is just going to be our convention, and positive and negative attract. And then for object B, we do KQB over R squared similarly, and that is also to the left. So when we're adding our two vector epsilon vectors together, we get just a bigger vector to the left, and it's newtons per coulomb, because that's saying like how much force do you get from just 1 coulomb of charge. It's saying how strong is that force field. Okay. So electric dipoles are a pair of equal and opposite electric charges with centers separated by a small distance. And the field lines for each charge is affected by the other charge, and it causes the lines to bend. So you don't just see this, like, it's not like spokes of a wheel anymore or radially going out. There's bending because they're close. And if you travel along this vertical line, which is equidistant to each charge at all points, although the direction of the line is always away from positive towards negative, so in this case always to the left, the density of the lines changes. So here the lines are more spread out, and then do you see how the lines are closer together here and then more spread out? So the force is weak and then strongest here and then weaker here. And just to reiterate here, and with all the previous slides, with point charges, the electric field strength depends on location. And now, so far we've only looked at situations where the electric field varies with distance from the charge, but now, instead of point charges, we have a charged parallel plate. So we have actually two parallel plates, a positive and a negative. And here, it doesn't matter where you are in between the positive and negative, you'll have the same electric field strength wherever you are between here and here. This is convenient for a lot of applications and experiments because it doesn't matter where you are. It's just sort of a background existence, this force field. This is convenient for a lot of applications and experiments, and you have one positive plate and one negative plate. They are equal and opposite charges, so it's a special type of a dipole. The electric field between the two parallel plates is uniform and perpendicular to the plates. The electric field outside the parallel plate is 0, so in reality, you do get bending of these lines around the edges, but many times the distance between these compared to the length is very small, so the plates go on, and the edge effect is not very significant. And for the purpose of this course, we just ignore that even exists. So outside, we have 0 electric fields, and inside here, we have a uniform perpendicular electric field. The value of, I said it's uniform, but the value of it is related to the charge here and here only. So this charge, positive whatever coulombs, is equal to that negative coulombs, and that is the only thing that determines the electric field strength. And what else was I going to say? Two applications of this is we've got the electrostatic precipitators. So if you look on page 343, or a capacitor. So we're not really going to study capacitors in detail in this course, but they're really, really important to know about if you continue on with anything in electricity and magnetism. So a capacitor is a device which stores charge. Okay, so example 4, a magnitude of the electric field between the plates of a parallel plate capacitor, so this is a capacitor example, is 1.8 times 10 to the 3 newtons per Coulomb. So that is our epsilon, newtons per Coulomb, force per charge. How would the field change if the plate separation were cut in half? Well, there would be no change because it doesn't matter where you are within the plates. And then the charge on each plate were to triple, well, epsilon is proportional to charge. So field strength would triple. So just glancing at all of these equations, so we've learned so many equations that look similar, and I always say when when two things are confusingly similar, put them right beside each other so you can see how are they similar and how are they different. So we've got for gravitational field, we've got the equation for force. For electric field, we have the equation for force if they're 2-point charges. And then the field strength for gravitational field strength looks similar to the equation we've said before, like the charge within the electric world is kind of like mass in the gravitational world. And then overall, whether you have point charges or not, force equals mass times gravitational field strength, or force equals charge times electric field strength. So you can see I think it helps to see them side by side. So although these equations, there's not too much for when you have to use these, it's mostly plug and chug, or when you have to rearrange, it's not too bad. So it's relatively simple math, but some common mistakes come in this unit from having very big or very small numbers. So your orders of magnitude, make sure you use scientific notation on your calculator, make sure you know where your buttons are. And also, whenever we learn a new equation, make sure you check when it's applicable. So these two here are only for point charges, and this would still be applicable beyond point charges if you know epsilon at a certain location. So for example, the parallel plate capacitor, you could use this. Okay, so it's time for you to do some practice questions. Please make sure to try all of them. And I was saying the one common mistake or a couple of common mistakes in this unit have to do with the orders of magnitude and making sure you're using equations when they're applicable. So the best way to check if you've got it is to practice and check your textbook solutions. Make sure you submit your exit ticket for this video as well. Submit these practice questions and have a safe and healthy day.